how this regarding neural networks and regarding neural networks and this RBM and their applications. Then we'll go for some this architecture of RBM, and then and we see how to train this RBM using energy-based model, and then convert to probabilistic model. Then the constructive divergence to calculate the error and everything. Then parameters. Then we discuss some parameters that are involved in this RBM. Then we'll go for applications. That collaborative filtering with restricted Boltzman machines, and then we'll go for handwriting classifications. Then other applications will just give a brief overview. Okay, so this is the outlines of my presentation. So the first generation, so these slides are borrowed from the slides from LinkedIn from Microsoft. So this the history of a neural network. If you go, we first see what is the perceptrons. So what they are doing in perceptron. Okay, in simple neural network in 1960s, what we are doing, we have that we are doing hand coded features and try to recognize objects by learning how to weight these features. Okay, so we have some input layer and some hidden layer and the output layer. And the output layer is some class labels. Okay, so labeling is here. So this neural network, we have input layer as well as output layer and some hidden layers. So here the learning has not been take place, but there are algorithms exist to learn the parameters, means weights in the neuron. Okay, but what happens after this neural network? That the next stage of improvement. There's so many that SVM. Okay, all of you know what is SVM. So this SVM it's a very clever type of perceptron. Then that hand coding of non-adaptive features, that means weights. Each training example is used to create a new feature using fixed reshape. Okay, so means you have to use SVM, how to class variables. And those things we are using for support for learning the weights. Okay, then how to decide? Then a clever optimization technique that we know support automation uses optimization technique is used to select the best subset of the features and to decide how the weight each feature when classifying a test case, how to weight. Okay, so but what happens here? Support vector machine has lots of advantage. But then after this, the back propagation. Okay, in neural network, if you see the previous diagram, this is one direction only. The learning not takes place, but then support vector machine still does some work. Okay, but still it has some pitfalls. So that back propagate algorithm, this is second generation of neural network around 1985. So what it does? The error is propagated to get derivatives for learning. So we have to this iterative process. All of you have known this. This is the iterative process, and the error is propagated to the backside, and the new weights are assigned with the old weights. And from the new weights are updated and as well as bias. Okay, so this is the second stage, the second generation of neural networks. So after this, we have seen there are lots of disadvantage of back propagation. So also there are techniques to handle those things, but this is some general statements. So if you see the back propagation, the output is labeled. Okay, requires labeled training data, but almost all data in real life is unlabeled. The learning time does not scale well. It is very slow in networks with multiple hidden layers, and it can get stuck. But these points are not, it depends upon our computer. The second point, and slow networks with multiple hidden layers, it also depends our computational resources. Then and also since it uses a gradient descent method, it has stuck in poor local optima. Then deep learning overcome these difficulties using undirected graphical model. So what we are today discuss regarding that RBM, it is an undirected graphical model. So actually what happens, we did not collect enough label data. For example, image, everything if you collect, it is not handwritten digits. So not enough label data. We don't have fast enough computers. Actually, we have nowadays, but still, for general purpose, we cannot. We don't have fast enough computers. We did not initialize the words correctly. So, if this problems, if you fix these problems, then this back propagation will work well. But this is the comment given by the Hinton in 2013. Okay, but nowadays the computational power increases, so you can use back propagation. At the same time, the new technique also overcome those things. Then, so we can overcome the limitation of back propagation. But the point is how we are calculating the back. If you go for the back propagation thing, there is a network, neural network. The final output is what is, suppose the image classification. So what is the probability of image, that one? So but not conditional. So image with this label. So this is not learned. So if you do this one, then back propagation techniques can be improved. Also, there exist so many improved version of back propagation. Okay. So, but our aim is not discuss here to regarding back propagation or its limitations and how to improve the back propagation, those things. But we'll move to the our topic. So after 1985, computers get the data sets, actually day by day data sets got much bigger. Okay, and computers also got much faster. The computer means computing power, and we found better ways to initialize the words of a deep net using unlabeled data. So the point is, although in back propagation we are using labeled data, so how to initialize the words of a deep net using unlabeled data. Unlabeled data, this is the main point. So that's why nowadays the deep neural networks are now state of the art for tasks like object recognition or acoustic modeling for speech recognition and many more also. So what that means, what is belief nets? So belief nets. So see here, belief nets, there is a difference between the neural network as well as autoencoder as well as belief nets. So a belief net is a directed acyclic graph composed of stochastic variables. So here, each node in this diagram is what we call it the neuron. So each node, okay, each node here where computations occurs is a stochastic variable, is a stochastic random variable, you can say. Okay, so we get observed some of the variables and we like to solve two problems. One is inference problem, another is the learning problem. So since this is a directed acyclic graph, composed of stochastic variables, but the inference problem is infer the states of the unobserved variables. So those variables which are not observed, okay. So how to infer those states? And second thing is that how this interaction between the variables, okay, to make the network more likely to generate the observed data. So how this interaction means weights, okay, weights. So how those things, the learning problem. So how the weights and bias, everything will be updated. So this is two things, but here it is a directed acyclic graph. It is a directed acyclic graph. So one direction only. So hidden to visible effects. Okay. So next one is Boltzman machine. So what's a Boltzman machine? It is a bidirectional. So once it is bidirectional, we can say, so direction has not, see the figure, direction has not been mentioned. Bidirectional means it is, we say both sides we can propagate. Connected networks of stochastic processing unit. So since all nodes have stochastic processing units, which can be interpreted as neural network models. A Boltzman machine can be used to learn important aspects of an unknown probability distribution based on samples from this distribution. So there are three here that H stands for hidden nodes and V stands for visual nodes. So whenever we provide the visual nodes V1, V2, V3, V4, so the suppose we know the distribution of the sample, then from this distribution, the distribution of S3, S1, S2, how they distributed can be computed, And again, based on the distribution of S3, H1, H2, S3, hidden nodes, the unknown prediction can be taken for the unknown visible nodes. Okay, but since it has both sides, both link exist between visible nodes to visible nodes, hidden nodes to hidden nodes. Okay, so there sometimes it gives biased result. Okay, since the link exists between H1 to H2, H1 to S3, S3 to H2. Okay, so and since if the node that means node means features. Okay, if the features has been more and there is a connection between the nodes is more, then the computational power also increase, and it takes lots of time to process those things. But what we'll do if we restrict something on this machine, then we have a easy computational power, and we can calculate the things that unknown distribution, unknown probability distribution based on these samples in an effective manner. Okay, so that what we call as by imposing those restrictions, we call Boltzman machine as a restricted Boltzman machine. So what are the restrictions we'll impose? So in Boltzmann machine, so what we'll do, it is a neural network type where this blue color H1, H2, H3 are hidden nodes, and V1, V2, V3, V4 are visible nodes. So we provide input to these visible nodes, and depending some mathematical formula calculation, we'll calculate the input to S3, and we make some, we generate some samples here depending upon some activation functions. Again, using those output, again will generate the distribution of these in samples. Okay, but here what happens, since the connection between the nodes, every node is connected to each node. So what happens? The computational cost will increase if you know there are many intermediate nodes. And the second case is since the hidden nodes are connected to each other, sometimes the output may be biased. So to avoid those things, if we impose some restriction on this, so if we remove these links, this H1 to S3 and H1 to S2, H2 to S3, then what will happen? Similarly, V1 to V4, V4 to V3, and V3 to V4. All are now independent. So once all are independent, then there is a connection between the visible layers to hidden layers, in where hidden layers are not connected to each other, as well as visible nodes also not connected to each other. So that restriction leads to the restricted Boltzmann machine. Okay, so that restriction, so the connection between the hidden nodes is not there, and the connection between the visible nodes also not there. So it leads to the restricted Boltzmann machine. So, so doing that, what will happen? Actually, since the hidden nodes are not connected to each other, so the output is not biased by some other output. Okay, so we see this one. So that is the main name. So imposing those restrictions, we get this is a special, and also will not make many hidden nodes, only one hidden node and one visible node. So these two restrictions make Boltzmann machines as restricted Boltzmann machines. And the point is that that autoencoder also behaves in this manner, same both side movement. But the point is here we'll deal with stochastic processing units. These all are random variables. But in autoencoder there are those are deterministic variables. So this is the main thing. And the second point is that in autoencoder, if you see, there is only one side bias is there for this hidden layers. But here we will see how that reconstruction means from hidden layer to how we are getting the back to the visible layers. Okay, the values for visible layers. Will not get the values, but rather will get the distribution. So let us check it. So come to the restricted Boltzmann machine now. So it is RBMs are shallow. They are not deep in the sense that only two layers we are considering: visible layer and hidden layer. Just like SBM and the hidden Markov model, those are shallow models. Okay, but deep neural is CNN, RNN. Those are deep neural, that more layers are there. So these are shallow two-layer neural nets that constitute the building blocks of deep belief networks. So we know the deep neural network as well as deep belief network. So but this RBM are the main block of deep belief network, and moreover, you can also integrate RBM with other deep neural networks. Okay, so you can get more papers on that one. CNN integrated with RBM like that. So the first layer of this RBM we called visible layer, and this second layer, this 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 layer, second layer is known as hidden layer. Okay, so each visible node takes a low level in feature. Okay, this is the input. We give a feature from the atom from a data set that to be learned. For example, if you have image, okay, so you give a single image as input. So once you give the input, each here it is a pixel. So these values are so it's a grayscale image. So the values are either 1 or 0. Okay, so this pixel value is either 1 or 0. So it is binary distribution 1 0 1 0 like that. So one image. So we have said how many that is size of the image. That many visible layers should be there. And hidden layer, we'll see how to find the number of units in the hidden layer. Let us say there is less number of it prefers that the hidden layer contains less number of nodes in comparison to visible layer. That depends how to classify. For example, if your image set has suppose it is that this restricted Boltzman machine is suitable for unlabeled data, but let us say you have no prior to applying this, you know how many different types of image you have. Let us say, okay, suppose you have an image data set, you have 4 to 5 classes. Then accordingly, each in you have hidden layers for 5 classes. If you have 5 classes, you have a hidden layer of 5 class. If you have 6 class, then you have a hidden layer of 6 class. Okay, so but just it is a 2 layer only, visible layer and hidden layer. So what happens? So each suppose one image we process here. So each pixel is now one pass to the one node, each pixel. Okay, so if your image size is 24 plus 24, then you have 24 visible nodes. Okay, so 20 here first image, how the computation has been expressed. This input x is multiplied with this weight vector. Okay, so then this weight vector multiplied. So we get one input to one output. We multiplied with this weight vector, we get some value. Similarly, from the second input, we multiply the weight vector and take the sum. Okay, so you can think that sum over wi xi. Okay, like that you can think it. So here each node. Okay, so I am moving from this to this. Okay, so this side. Okay, so if you see the first node is connected to all 3 hidden nodes, first visible layer node. Similarly, the second visible layer is connected to each hidden node nodes like that raised to. So so for each visible each edge connected edge, there is some weight. Okay, initially you have to assign some weight, and how to assign some weight, that is also some methods are there. So let us say you know some initial weights you have assigned here. Then these weights are multiplied with the input x, and again this weight is multiplied with the second input, and similarly all 3 will be summed up. Then addition with the bias value b, bias vector. Then it passed through an activation functions. The activation function may be anything. For this time being, you may assume that sigmoid function. Okay, and this activation function that converts this probability value to one binary values depending upon that activation function you will get. You pass through that value through the activation function, and that activation function depending upon some distribution of the output, you may define some threshold. So accordingly you may convert to either 1 or 0. So if it is image, so you have a binary distribution, binomial distribution here and here also, that 1 0 1 0. So so this is one type. So if you have continuous, then you have here Gaussian distribution. Similarly, what is your output, binomial or Bernoulli, like that you can think. So Bernoulli distribution here 1 0 1 0. So here 1 0 1 0. So true false true false. So So if you have no, if you say your input is continuous, you may think some Gaussian distribution or normal distribution, no problem. You can give it, the distribution becomes normal. Then similarly, here that time the computational process, the formula little bit change, but the process remains same. So this is I think it is clear how this activation function, and the point is how to choose this activation function. That is another point. So weights as well as input. So you are calculating the value of the hidden layer. Once you calculate the value of the hidden layer, okay, then here there is no class. Okay, there is no class. So it is different from that back propagation, everything what the class is there. So from here in back propagation or something, here we are doing if the value is something, then this belongs to this class or this belongs to this class. Okay, but here it is not like that. So here this value, this activation function value here. Now we have, so once these are two-side computation. Once we have this is the feed forward side, okay, from visible layer to hidden layer computation. And once we get this output from this output, okay, from this output, again we will compute this input values. Okay, this process will continue several times. Okay. So we have three things. Initially, we give inputs. Okay, so we calculate the hidden, we process the value, and we calculate this output. Okay, again from this output, you will reconstruct back what are the corresponding input. Okay, so what happens? So these two. So we are here input and here we are calculating. So accordingly, we will find the errors. Okay. So this is hidden layer. Okay. So this is multiple inputs, and we have single one visible layer and one hidden layer. So here, see, we have, if you have multiple hidden layers, what you have to do? If you have multiple hidden layers, then it is not like that. What happens here? So since RBM works with only two layers, okay, visible layer and hidden layer. So if it has multiple hidden layers, then what will happen? Initially, the computations occurs these two, okay, first visible layer and first hidden layer one. Once these weights and everything are optimized, then this hidden layer acts as a visible layer and to the hidden layer 2. Okay, acts as a visible layer to the hidden layer 2. Similarly, if there is another hidden layer, once this weights everything is optimized, then hidden layer 2 will act as an the output of hidden layer 2 act as an input to the hidden layer 3, like that. Similarly, when reverse computation happens, so from hidden layer 2, we will reverse compute to hidden layer 1 and optimize those bias as well as weights. Then once this optimization has been done, then from hidden layer 1, just we are doing in the previous slide, again we are reconstruct the initial sample and check that how much error, or what is our initial sample and what is the reconstructed sample, and how much they have differ. So that is the cost function here. Okay. So for example, this is an image. The first input is an image, suppose a cat image. Okay. So every pixel is input here. Okay. Every pixel you got some output. Again from this side you construct some you reconstruct back. You get some distribution. Now find the difference between the initial distribution and the final distribution. So this is all about restricted Boltzmann machine. So we'll go, that is the thing only. So what is reconstruction? So already I have explained this reconstructions. Reconstructions means here. So from hidden, initially this is feed forward. Again another one is feed backward. So once we from visible layer to hidden layer, this is feed forward. Now from output from hidden layer, we'll compute the original sample. That is the feed backward. So, but there is some bias, okay? So same formula, but there is this bias. So from both side computation, hidden layer, visible layer to hidden layer, as well as hidden layer to visible layer. So this reconstruction, once we got a reconstruction, then when we will stop and something, so what is the cost function, how to minimize those things. So this is all, this is the, so we have one sample here, since this is your stochastic, okay. So we have one sample, and from reconstruction, we will obtain another sample. Now we compare these samples, okay. We compare these samples, and such that they are very close, the distribution are very close to each other, then we'll see that okay, the model, the weights are updated, everything will be okay. If the distribution is not very close, then we'll repeat this process. Still we get some up to some approximation. Okay, some error is will be there, but it is up to some correctness. So for that, to del 2 distribution, so what RBM does, it is based on energy based model. So what is energy based model? So it is, so we have two layers, visible layer and hidden layer. So we have a joint configuration between visible layer and hidden layer. So this joint energy is given by this equation, AI Vi minus Bj Hj minus Vi Hi Wij. So if you see AI Vj, so here VAI is the bias of visible node. Each visible node, we multiply this one, AI VI. And similarly, this is the for hidden node. And again, this part, Vj Hj, okay, and Wij. So this Vi Hi are the binary states of visible unit, and hidden unit J. AI B are their biases, and W is a weight between them. So this is the energy function. So what happens? The training of RBM consists in finding of parameters for given input values so that that energy reaches the minimum. So